Hello, everybody. Thank you very much for joining me here on this chilly Thursday evening to talk about this elusive substance called dark matter. Now, if I'm honest, this talk could be very quick because talking to you dark matter, we don't really know, we can't see it, we don't really know what it is, we're not probably 100% sure that it exists, so this could actually be a really quick talk. So the first things I'm going to do is to try and convince you that it exists, talk to you about why we think dark matter exists, and then talk to you about some of the candidates that dark matter could be. As I've been introduced, I'm Dr. Elizabeth Cunningham. I work for the Involve Foundation, which manages ScienceWise. So my day job is talking to people, doing public engagement with science and getting the public involved in participation in research and in scientific policy and technology development. I'm also a visiting researcher at the University of Surrey, where I did my PhD in nuclear physics. That's my research background. And then I should also confess that I used to work at the Royal Observatory, Greenwich. So after I finished my PhD, my first job was Planetarium astronomer at the ROG, which was a good fun job. So that's me in a nutshell and how I've been invited to talk to you tonight. So I'm really looking forward to talking to you about dark matter, and there will be an opportunity, I believe, to ask questions at the end. So I think you can use the chat function to type questions, and then I'll do my best to answer those at the end. But I must confess, as I said, we're not exactly sure about what dark matter is, so it might be tricky to answer some of your questions, because probably astronomers and particle physicists are still asking that question themselves. Okay, so dark matter, why we think 95% of the universe is missing. So what do I mean when I say 95% of the universe is missing? If 95% of the universe is missing, what's the other 5%? So the visible matter that we can see in the universe only makes up about 5% of the universe. So what do I mean by visible matter? So by that I mean all the ordinary things, all the things that astronomers look at. So stars, planets, moons, galaxies, comets, asteroids, nebula. All of these objects are made of visible matter. So they either emit light, they reflect light, they obscure light, and they're all made of the same stuff that we are made of, atoms. Just so we're all on the same page, I'll talk to you about what an atom is. So this is a stylistic view of an atom. So atoms don't actually look like this. But we have the two parts of the atom. We have the electrons orbiting around a central nucleus. And as a nuclear physicist, it's the nucleus of the atom that I'm most interested in. And then there are two particles in the nucleus, protons and neutrons. So when we learn at school about what stuff is made of, we learn that everything is made of atoms, but in fact that isn't actually true. As far as we know, only about 5% of the known universe is made of atoms. And so 5% is visible matter. The substance I'm going to talk about today, dark matter, we think makes up about 26.8% of the universe. And then another even more exotic and weird substance called dark energy, we think makes up 68.3% of the universe. So I'm not going to talk very much about dark energy. You could have a whole lecture series on dark energy and the evidence for and what it could be. But I will just talk a little bit about why we think there's this other thing, dark energy, in the universe. So if we look back at the expansion of the universe, of our evolution of our universe, so we think the universe is 13.77 billion years old, and that it started at a big bang, and that the universe went through a period of rapid inflation, and then it has been slowly expanding ever since. But in 1998, two astronomy groups were looking at the speed that faraway galaxies are moving away from us, and they're studying distant supernova, and they actually realized that instead of just expanding, the universe was actually accelerating. So distant objects were accelerating away from us, and this goes against what we sort of understand about the nature of the universe, the rules, the general relativity that Einstein came up with. And so what that implies to us is there's something going on that we don't quite understand that is fighting against the force of gravity and actually making matter making the universe accelerate away from each other. So the expansion of the universe is accelerating. So this kind of repulsive force that's causing that to happen. And so because we don't really know what it is, we call that dark energy. So dark energy is responsible for that accelerated expansion of the universe. And the only thing really that it has in common with dark matter is that we don't know what it is and that we can't really explain it. So dark matter we discovered first, it's got dark matter and we think it's some kind of matter, and then dark energy we don't really know what it is. So yes, that's even more elusive. So we have to ask the organisers of the talk to maybe organise another talk on dark energy at some point, but today we're focusing on dark matter. So we're going to talk about this 26.8% of the universe and why we think it exists. So as I've said, we can't see it. We don't really know what it is, and it is a little bit embarrassing that, given thousands of years of observing the heavens and decades of modern astronomy, we still don't know what 95% of the universe is. But luckily for us, it's these kind of mysteries that get scientists and astronomers out of bed in the morning, gets us excited about trying to understand the universe. And also, if there's still problems to be solved, then we still get employed to be scientists and researchers. So that's also very good. So while it is a bit embarrassing that we still don't know what 95% of the universe is, it also is an amazing question that we get to study and figure things out. So what am I going to talk about? What is dark matter and why do we think it's there? So this is a picture of galaxies, and it shows a simulation. The white cloud shows a simulation or a modelling of a dark matter cloud that we think is there. Now, what is dark matter? In the strictest sense, it is matter that is dark. So we can't see it. It doesn't interact with light. It doesn't shine. So the first piece of evidence we know for dark matter was by looking at how galaxies rotate. So you have a spiral galaxy like this, and the stars in the spirals rotate around the centre of the galaxy. But if you calculate how you think the stars and the edge should be rotating based on the amount of mass that you can see in the galaxy, we find that galaxies don't rotate like they're supposed to. So if we look at a graph of this, we look at the galaxy rotation curves. So we've got the velocity of the stars against the distance from the centre of the galaxy. This curve that you can see now is what you would expect. Well, we actually measure the speed of the stars doing that. They're going much faster than we expect. So that would imply that there's more matter in the galaxy than we can actually see. So again, to solve this problem, to solve the problem of the accelerating expansion of the universe, we created dark energy to try and explain this galaxy rotation curve that we don't quite understand. We created a substance called dark matter. And so we think that in galaxies, around in the outer edges of a galaxy, we have what we call the dark matter halo. So there's matter that's there that's causing the stars to move faster through space, but we don't know what it is. And you can sort of think about it as it's like a structure in the galaxy holding the stars in place. So I use this analogy. If you look at the New York skyline at night, you can see all the windows are lit up, but you don't see the buildings, the dark structures that are holding those lights in place. So that's an analogy to dark matter. Basically, the dark matter is surrounding the outer areas of these of galaxies and causing the stars to move much faster. So that's the original evidence for dark matter. We also have other pieces of evidence for dark matter. So we could also use the bending of light by massive objects to see or to find where we can't see dark matter, to find where dark matter is. So this is a lovely picture from the NASA website of an Einstein ring. And Einstein's theory of general relativity postulates that mass, or it shows that mass bends light. It affects the trajectory of light through space. So if you have a really massive object in front of a big object behind, so in this case we have a really, really big red galaxy, luminous red galaxy in the foreground, and we have a blue spiral galaxy in the background, and the light traveling
from the blue spiral galaxy in the background is distorted, is bent by that huge luminous red galaxy and causes the light to form this ring. Now, Einstein rings are relatively rare. What you usually get through this bending of light, what we call gravitational lensing, you usually get multiple images of the same galaxy in an image. So again, you can do this experiment later when you have your tea, if you have a glass of wine. If you draw a black dot on your tablecloth and then you move the bottom of the wine glass over the black dot, you can see that the bottom of the glass distorts the image, and it creates, even though there's only one black dot, it makes it appear that there's multiple images. And this is basically what the matter does. So it bends the light, creates this gravitational lensing effect, and it splits the image of the distant galaxy. So at the beginning of this section, when I was started talking about dark matter, I showed you this dark matter map. And this is a really lovely image from Hubble, and it actually shows only 42 distinct individual background galaxies, but there are actually 135 lensed images in this picture. So lots of the galaxies have been split, or the light has been split, the images of them have been split. It makes it look like there's multiple versions of the same galaxy, which tells us that there's a lot of matter lying between us and these background galaxies, which is bending the light, causing this gravitational lensing and creating 135 galaxies where there should only be 42. And so from modeling this lensing, the gravitational effect that's causing it, we can create this simulation of the matter that we think is lying between us and the galaxies. So that's what we're looking at here. So the white cloud is a simulation of the dark matter that we think is causing this gravitational lensing. So yes, this is the visible galaxy, and that's the dark matter. So that's another, so gravitational lensing, the way that dark matter bends light, has a gravitational effect on light, is one way, another way that we can detect it. Another evidence for dark matter is by looking at the large scale structure of the universe. So here we're showing a simulation of the cosmic structure. So all the points of light here are in this picture, and the nodules are galaxy clusters. They're clusters of galaxies. And I always like looking at this image. See the large scale structure of the galaxies in the universe. And I always think how similar it looks to sort of biological things, like it looks like a neural network or neurons. And I always think there's something, as a nuclear physicist, there's a lot of sort of symmetry between the very small and the very big. But here we're seeing sort of a symmetry between the massive, large-scale universe and also biological systems in our body. So I think that's just a sort of aesthetic reflection. But yes, back to dark matter and evidence of dark matter. So also, if we look at galaxy cluster collisions, we can find evidence for dark matter. And the bullet cluster, I think, is probably one of the most sort of poetic, beautiful examples of evidence for dark matter. What this picture is showing, the bullet cluster, you're seeing two clusters of galaxies that have collided and passed through each other. So this would have been a massive, highly energetic event. So, you know, probably the most energetic event the universe had seen since the Big Bang, two massive galaxy clusters colliding. And the colours are put in, they're artificial. So what we're looking at here is the pink cloud represents hot gas, normal matter, that 5% of matter. And then the blue colouring shows dark matter. And again, the dark matter is being inferred here through gravitational lensing, through calculations of how the light's being affected. And basically what's happened is these two galaxy clusters colliding have sort of acted a bit like a sieve. So, you know, you've got a huge amount of matter colliding. So all the normal matter that is gravitationally attracted by a normal amount has been slowed down by this collision. But the dark matter that only very weakly interacts with normal matter has just gone traveling through at the same speed. So it's basically acted like a dark matter filter, this galaxy collision. So the dark matter has continued moving, not really noticing that this energetic event is happening, these two galaxy clusters are colliding, whereas the normal matter has been slowed down. And so this is what is called the bullet cluster, after this sort of bullet-shaped pink normal matter cluster there on the right of the image. But yes, so because of this process, the dark matter has been separated from the normal matter, and then we can see through gravitational lensing where it sits and simulate where it sits. So the bullet cluster is quite a nice, beautiful example of another reason why we think dark matter exists. And then the final piece of evidence I just want to talk about is about talking about the cosmic microwave background. And so this is the radiation left over from the creation of the universe. It's actually accidentally detected in one of my favourite stories in the history of science by a radio telescope in New Jersey, at the Horn antenna, which is pictured here. And they basically built this massive radio telescope to do astronomy, and they kept finding this sort of low-level background noise that they couldn't get rid of, and it was visible wherever they pointed, wherever they looked in the sky. They found this low-level radiation, and they did all sorts of things to try and get rid of it. There were pigeons nesting in the telescope, and they got the pigeons out. They thought maybe the droppings that the pigeons had left were somehow creating this. They cleaned the telescope. They did all these sorts of things, and they could never get rid of it. But what they actually had discovered by accident was this low-level background radiation left over from the radiation, whereas actually they thought they were getting interference from pigeon droppings. So it's one of my favourite stories. Anyway, so if we look at the cosmic microwave background, which is the radiation left over from the Big Bang, so this shows very, very small irregularities in radiation. So the colouring, it looks like there's quite a lot of variation across the whole of the sky, but actually the variation is only 1 part in 100,000. So the fluctuations shown in this picture are very, very small. If you do analysis in the irregularities in the cosmic microwave background, you can see it indicates, because dark matter interacts with radiation differently to ordinary matter, you can look at the gravitational effects and you can simulate how much dark matter you think is in the whole universe by using the cosmic microwave background. And that's where we get this number of what percent we think of the universe is. So we think that 5/6 of the total matter in the universe is dark matter by analysing the irregularities in the cosmic microwave background. So based on all these pieces of evidence of dark matter, what do we know about dark matter? So we know it doesn't give off light, that it's dark, does what it says on the tin. It interacts very weakly gravitationally. You know, if you have whole galaxy clusters colliding, it still just carries along merrily. It's not slowed down that much. It does have a gravitational effect. You know, it's very small, and it makes up 27% of the universe. So what could it be? There are lots of different candidates for what dark matter could be, and we're going to have a look at each one of these in turn now. So one of the simplest theories that people often say to me is, oh, surely couldn't dark matter just be matter that we can't see? You know, like, so black holes don't give off light. You also have neutron stars, brown dwarf stars that were never big enough to shine, white dwarf stars left over when stars like our sun have died or made these, and these are called machos. So these are massive compact halo objects. There's a lot of funny acronyms in dark matter. Machos is a good one. We'll have another one in a bit. Also, could they just be planets, free planets, you know, moving through the universe? Could this be what dark matter is? And there is some evidence that machos, or this sort of ordinary matter that you can't see, could make up a small amount of dark matter, but it would be really a tiny fraction, and it's not enough to explain the amount that we see in the universe. So another possible theory is that it could be antimatter. So antimatter, antimatter is so every matter particle. So for example, the electron that we saw earlier whizzing around our atom has an antimatter partner or particle. So for the electron, the antimatter particle is a positron, and when those two particles meet, they annihilate and give off a signature type of radiation that we can measure. We can find the wavelength of. So one example is that, you know, maybe dark matter could be antimatter. But if there was a lot of antimatter flying around the universe, eventually it would interact with matter and it would give off large amounts of radiation, and we'd see this leftover radiation from this annihilation in the universe, and we just don't see it. So we don't think, maybe some is antimatter, but we don't think enough, because if there was this much dark matter in the universe, we'd see, where is the radiation? We'd see a lot of radiation. And then there's a lot of exotic particles. I think particle physicists enjoy inventing new particles to solve a problem. So there's all sorts of different types of particles that we have that could be candidates for dark matter. I think most of my friends and colleagues who hunt for dark matter think the most likely candidate of all these different types of particles is the WIMP. I told you there are some good acronyms in dark matter. So WIMP stands for weakly interacting massive particle. So if dark matter does what it says on the tin, this also does what it says on the tin, because basically that's what we want to find to explain dark matter: a weakly interacting but very massive particle to explain all this particle. So WIMPs have been theorized for a long time. We expect them to be everywhere, but they just don't interact. So, for instance, if you held up your hand, every second you would have 20 million WIMPs passing through your hand. But because they're so weakly interacting, you'd only have maybe one per month hitting a particle in your hand. So most of the time, the WIMPs just travel through matter and they don't interact. So that's what we think one of the candidates could be for dark matter. Another candidate is the axions. This is another hypothetical particle that has sort of been theorized to explain the difference between matter and antimatter. So obviously we're made of matter. Most of the universe that we observe, or the visible matter that we can see, is made of matter. But our theories of the Big Bang, of universe creation, say that there's the same amount of matter and antimatter should have been created in the Big Bang. We can't really explain why what we see is matter. And so axions have been sort of theorized to help explain this difference between matter and antimatter. And we would expect to find them at the center of the sun. They would interact even more weakly than WIMP, so they'd be even harder to find. And they also have less mass, so there would need to be more of them to explain dark matter. So that's another candidate. And then, so that's the axion. And then the gravitino, now we really are making up words. The gravitino is the partner particle to the hypothetical partner particle to the hypothetical graviton that we theorize transmits gravitational force, but we haven't found the graviton. So it's quite hard to write a research funding request to find a hypothetical particle partner of a hypothetical particle. Well, I've got a bit of a tongue twister there. So there are people thinking about gravitinos, but we'll probably have to find the graviton first if we're gonna, if that is the source of dark matter. Another theory is that it's just a problem with gravity. So, we're having now, to keep Einstein's theory of general relativity, we're having to invent dark matter, we're having to invent dark energy. Maybe our sums are just wrong. Maybe what we think how things work is wrong. And that is a very real prospect, and lots of different modified theories of gravity have been proposed. One of the front runners is called modified Newtonian dynamics. And usually when I up until recently, when I give this talk, I would sort of be quite dismissive of these theories. But recent results from the James Webb Space Telescope has been looking at the evolution of early galaxies. So our current theories of cosmology and how we understand how the universe has evolved indicates that sort of dark matter drives the evolution of galaxies. And the further you look back, the early galaxies should be sort of smaller and dimmer. But what JWST sees, this new space telescope, which can look further back into the universe than we've ever been able to look before, it actually sees galaxies that are much bigger and brighter than we expected. So it means that our theories of galaxy evolution involving dark matter aren't quite right. And actually, the results correspond to this modified theory of gravity, this modified Newtonian dynamics. So this modified theory posits that that when gravity, the further away, that when gravity becomes extremely weak, so the further away you are from mass, that gravity begins to behave differently. And so you wouldn't need dark matter to explain galaxy rotation curves with modified gravity. You could explain it by gravity behaving differently when it's weaker. And as I said, there have been some success in modeling galaxy rotation curves with this theory without dark matter, and it does also explain why we're seeing these bright larger galaxies. JWST is seeing these bright large galaxies. It doesn't explain everything, so it can't explain what we see in the bullet cluster. So I think if this is indicating that gravity needs to be modified, this isn't the theory that explains everything, but it could be that. I mean, so what basically is, it's basically still an unknown, and what they basically said in the end of the paper is that the fact that this galaxy, looking further back at these galaxies, JWST looking further back in time at these galaxies that are brighter and larger than we expect, that is telling us something, and the fact that it corresponds to this modified theory of gravity is telling us something, but what it's telling us remains as mysterious as the composition of dark matter itself. So there's something going on, but we're just not sure what, which is a lot of what this talk is about. There's something happening, but we're not really sure what's going on. So that's definitely, I used to be much more dismissive of that than I am now, based on these new JWST findings. Okay, so we've got some candidates. If it does exist, how do we hunt for dark matter? And there are lots of different experiments all across the world hunting for dark matter, but there's sort of three ways. Basically, there's looking for it directly, indirectly, or in a lab. So the first place we're going to hunt for dark matter tonight is in space. So there's an experiment on the International Space Station which is studying cosmic rays, high energy particles from space. And they analyse about 25 billion cosmic ray events in 18 months. And they're looking specifically for ones with a different signature that are caused by antimatter particles. And we think that some small portion of what these antimatter particles, these cosmic ray that are caused by antimatter particles, we think that some small portion of them have been influenced that are caused by dark matter. So we're looking at sorry, that's the experiment. We're looking for specifically for the antimatter particle, the electron, the positron that we talked about before. And what this experiment has found is a whiff of dark matter. So basically, one of the candidates for dark matter that I haven't talked about yet, the neutralino, collisions between neutralinos would cause a large number of positrons, cause a large amount of antimatter. And so if we can find evidence of these this antimatter being created through this process by looking at cosmic rays, we should be able to get a whiff of dark matter. So that's what this experiment on the International Space Station is doing. So far we're seeing enough cosmic rays caused by antimatter that we think, you know, that this is still a candidate. But some people also think that these results could be explained by pulsars, which spin and basically also throw off high energy particles and positrons as well. So we need more data from this experiment to determine whether these antimatter particles, the cosmic rays caused by antimatter particles, are from neutralinos or from pulsars. So that's one to watch. AMS experiment on the International Space Station. We also do these experiments on Earth. So this is a picture of CERN, the big European particle physics experiment on the French-Swiss border. Beneath the ground, these lovely French and Swiss towns, is the Large Hadron Collider with 4 experiments around the edge. And it's the ATLAS experiment that is we're using to look for dark matter. Now, this is a very famous picture of ATLAS. And the irony is this is a picture of where ATLAS goes. So this is the ATLAS cavern. It's not actually the ATLAS detector because it's not been put in yet. But people often use it as a picture of ATLAS. So we have a massive detector in this cavern. And basically Atlas has been created to capture, so we have high energy particles whizzing around the LHC, they collide, they break up, they generate energy. And the Atlas detector has been designed to have different layers of detectors that stop, they capture all the particles and all the energy from a reaction. So they should, if the reactions occur as we think they will, they should capture all the energy. And so what Atlas is also looking for is any missing energy, because it should, you know, if the reaction's occurring with normal matter, it should capture everything, and the energy going in and the energy coming out should balance. But if we ever find that there's an imbalance, there's some energy missing, that could mean that the reaction has generated dark matter, and it's the dark matter that's gone out of the detector because it's very weakly interacting. So people are scouring through all the terabytes of data that the LHC has produced to try and find if there's any reactions where there's missing energy. And there's also another cool experiment at CERN, which I only learned about recently, although I've been to so many times, I never learned about this. So I talked earlier about axions here in our candidates. So these are hypothetical particles. So this detector at CERN called CAST is combining, it's like a particle physics, it's like a particle physics telescope. So it's combining elements of the LHC and astronomy telescopes. And basically what it's trying to do is designed to detect axions from the sun by having a layer. So it has a layer which reacts with the axions, turns them into X-rays, and then there's an X-ray telescope in there to detect the X-rays, which should make them easier to detect. Again, they haven't detected any yet, but they're still looking at the sun, and I think it's just a really nice, cool hybrid of particle physics and astronomy. It's like a particle physics telescope, which is pretty cool. And then how I got interested in this whole dark matter topic in the first place was that we also have experiments deep underground looking for dark matter. So this is my picture on my first slide. This is for direct dark matter detection. And in Yorkshire, we have the Balby Underground Laboratory. So it's in a potash mine on the North Yorkshire moors, and it's 1.1 kilometres underground. And so when the scientists, so I've been there a few times, and when you get in the lift to go down to the lab, you also get in the lift with all the miners. So it's a very interesting cross-section of society, the particle physicists and the miners going down a lift together and having a chat. And so the miners go off in one direction to do their mining, and then the scientists go off in the other direction, as I said, 1.1 kilometres underground. Scientists go in the other direction to this state-of-the-art lab where we have had a history of some of the best dark matter detectors in the world. So these are two of the detectors that used to be down in Balby, and these are looking for WIMPs. So these are detectors that are filled with noble gases to try and they're underground to try and get rid of any of the other kind of background interactions that could interfere with dark matter detection. So they're underground, so there's no cosmic rays or any reactions coming from the sky or from space. The labs are built to try and minimize any kind of background radiation. The detectors have layers of protection, and then are super sensitive right at the core to try and detect these really, really weakly interacting particles. And so Drift 2 and Zeppelin 3 are two historic detectors that have done this. The new one, which started up in 2022, is called Lux Zeppelin. It's building on these generations of detectors. And this is hosted at the Samford Underground Research Facility in South Dakota, also built, I think, in an old mine. This is where all the dark matter scientists hang out. And it is the world's most sensitive dark matter experiment. Unfortunately, we keep building these bigger and bigger and better detectors. We still haven't detected dark matter. We still haven't had that signal to indicate that a WIMP has been detected. But all the effort and information is not lost, because basically we have our models of where we think WIMPs should be, how they interact and how they what their energies and masses are, where they think they exist. So every time we build a detector and fail to find one, we're narrowing down on the range of where we think WIMPs should be. So the next generation, or the generation after that, of WIMP detectors should should basically, we'll be able to rule out, even if we never detect a WIMP, we'll be able to rule them out as a candidate for dark matter. That's what I'm trying to say. So even though we've not had a positive response yet, a negative response is still a result. And dark matter still, captures people's imagination. So we're still searching, we're still in the news, we're still looking for 95% of the universe. It's a problem that still excites people. As I said, this JWST result may upend our models of the universe. There's always new things happening. It's a really exciting time to be in astronomy. And so while it is, a bit embarrassing, we don't know what 95% of the universe is, it's still the problem that gets us all out of bed. And we've decided, instead of to be ashamed of our ignorance, we've decided to celebrate our ignorance. And so in 2018, someone decided that dark matter would try and hijack Halloween, and we would make the 31st of October Dark Matter Day. And so we do all sorts of public engagement and events on Halloween to try and promote this exciting field of science and to get people excited by the mysteries of the universe. So we give talks, we do activities in Parliament, we do school workshops. School workshops are always a bit disturbing on dark matter, because once you talk to children about dark matter, they always create these particles that like destroy the universe, or evil particles that destroy the moon. So I do try and encourage them to create, happy dark matter particles that are beneficial to Earth and the universe. But I think it's a bad name. Dark matter just makes people think that it's evil, but it's not. It's just an unexplained question that we don't know. We can't explain what's causing the things that we observe in the universe. And so it's not great that we don't know, but everybody loves a mystery. We're all still having fun. All dark matter physicists are still having fun trying to find dark matter, and hopefully one day soon I'll be able to give this talk and actually finish by telling you what dark matter is. And whatever the team or the consortium or the collaboration that finds dark matter will definitely be in store for a Nobel Prize. It's probably the next big discovery that everyone's waiting for in physics. So thank you for persevering with me today. That is the end of my talk.